Hello, everyone, and welcome to the Applied AI seminar series. Today, I'm going to be talking about fine-tuning with RAG for healthcare applications. So why do we need specialized AI in healthcare? There's hugely complex medical data which needs to be encoded. So this is vast and a rapidly evolving field. There's specialized terminology and concepts, and there's an interdisciplinary nature of modern medicine. So it's critically important to be accurate in what we provide for healthcare recommendations. So this has a direct impact on patient care and safety. There's a need for up-to-date evidence-based information, which reduces risks of misinformation. There's a need for having personalized solutions, which are tailored specifically to individual patient needs and which incorporate the latest research and treatment options. So this is necessary for precision medicine initiatives. Enhancing healthcare professional efficiency is definitely needed, considering the need for more medical staff and the increased workloads that medical staff are facing. Having quick access to relevant medical literature is important. Providing assistance in diagnostics and treatment planning is essential. This can be a huge time-saving initiative for research and information retrieval. And just in terms of bridging knowledge gaps, doctors are only human. So providing them with information which might be disparate or which might be hard to find in a more efficient way is going to be fundamental to making sure that patients receive the best care possible. By providing solutions like this, we can ensure that we're utilizing ethical solutions in that we're providing the most up-to-date resources to a physician at a given time. For today's seminar, I'm going to go over fine-tuning Llama 3.1, which was previously Meta's largest large language model with 8 billion parameters. It has improved performance over previous versions. It's an open weights model, which allows for fine-tuning. So this model is accessible to anybody. All you have to do is register to pull the weights, and then you can utilize this model for your own applications. So I'm going to be going through fine-tuning, which is the process of adapting the pre-trained model weights. So this would enhance performance on a specific task or domain, which would require less data than training from scratch. We're going to take a corpus of data and we're going to pass this through the Llama 3.1 model. And ultimately, we're going to fine-tune the weights to make sure that we have an expert model that can answer medically relevant questions. So I'm going to be doing that with the PubMed QA database, which is a collection of 1,000 medical research questions, which are expert written answers based on PubMed abstracts, and it's ideal for training a medical AI assistant. The goal here is we want to create a specialized medical AI capable of answering complex healthcare queries. The recommended hardware for this task, I would recommend utilizing an A100 if possible with 40 GBs of VRAM. So this would allow for efficient training of an 8 billion parameter model. Some of the key libraries that we're going to be utilizing in the roles are the transformer library, which provides pre-trained models and fine-tuning utilities, the datasets library, which provides efficient data loading and pre-processing, the perf or PEFT library, which is parameter efficient fine-tuning techniques, where we're going to be utilizing a technique called LoRa, TRL, which is a transformer reinforcement learning package, and Onslaught, which provides optimizations for faster and more efficient fine-tuning. With GPU acceleration, it's going to enable us to handle large models and data sets. We're going to be working with a 4-bit quantized model and mixed precision training. And in terms of the Python environment, we're looking for something with Python 3.10 or greater and CUDA 11.7 or greater for GPU support. In terms of preparing the model, we're going to be utilizing the Llama 3.1 8 billion parameter model, which we're going to be loading from Onslaught. So we're calling it as Onslaught slash MetaLlama 3.1 8 billion parameter B&B quantized 4-bit. So this is pre-quantized for efficient loading. It utilizes 4-bit quantization, which means we're taking a reduced representation of the model, which reduces the memory footprint by 75% compared to floating point 16, and it enables fine-tuning of larger models on limited hardware. We're going to be utilizing low-rank adaptation. So that's the rank of LoRa update. 1 second. The target modules that we're going to be utilizing are listed here, and it covers both attention mechanisms and feed-forward networks. We're utilizing ring-stabilized LoRa, which improves training stability, especially for higher ranks. And we're utilizing gradient checkpointing, which allows for larger batch sizes or model sizes and trades the computation for memory efficiency. So the data set that we're utilizing to fine-tune the model is the PubMed QA data set. And the structure of this data set is there's some context and a question and answer. So the context is relevant medical literature excerpts. The question is based on that excerpt. So it's a research or clinical query with an answer, which is an expert written response. And we're going to load this data set from the Hugging Face data set package, and we're going to format each entry into a conversational structure, apply a chat template for consistency. So the chat template ensures uniform input format for the model, and it prepares the data for instruction following tasks. We're utilizing a chat ML format where you have a human and an assistant. So the total entries that we're going to be utilizing are 1,000. So these are some of the training configuration arguments that we're utilizing. We're going to be utilizing a learning rate of 3e to the minus 4. We're utilizing linear decay for the scheduler. We're going to be running for a single epoch, which is a single pass through the data set with mixed precision. We're utilizing a paged AtomW optimizer, which is a memory efficient variant of Atom. And we're implementing a weight decay and 10 warm-up steps for gradually increasing the learning rate. The sequence length that we're working with is going to be 2048 tokens, and we're utilizing a fixed seed. So in terms of the fine-tuning process, we're going to load and pre-process a batch of data. We're going to do a forward pass through the model, calculate the loss, accumulate the gradients over 8 steps, update the model parameters, and repeat for the entire data set. Again, we're utilizing 4-bit quantization, which is going to reduce the memory utilization by 75%. We're going to look at loss curves, the learning rate, scheduler, and aim for high GPU utilization. It's also good to monitor the memory in particular. And in terms of model saving and loading, it makes sense to merge the LoRa weights to combine them into a single updated model and save the model locally. So we're going to be doing that as well. We're going to be applying a chat template for consistent input formatting to make sure that queries are formatted identically to make the training set data. I think it makes sense at this point to jump into the actual code. Let me pull the code up here and we can actually take a look at it. So this notebook goes through fine-tuning. Basically, we check for a GPU to make sure that it's available, and then we utilize it appropriately. We load and prepare the model. Can you see my VS Code now? So again, we do some package installs, some imports, and check for GPU. And then we actually load and prepare the model. So again, we're utilizing the Unsloth version of the Meta Llama 3.18 billion parameter 4-bit quantized model. So it's very simple to load this and make it available for utilization. So we load it and then we prepare it for fine-tuning with LoRa. And it's pretty simple to set this up. It takes just a few minutes to actually load and prepare the model. And then in terms of preparing the data set, we have a couple of functions here for formatting the PubMed QA data set into a structure which is human and GPT responses. So we apply a template to this data set, and then we can actually utilize it to train the model. So we go through here and we display what the data looks like. So we have a context, and then we have the rest of the data. So in terms of setting up training and actually implementing the training, we utilize the SF trainer package where we pass in a number of arguments, and it's as simple as just saying trainer.train. Once that's initialized, we go through and we look at the training loss over a number of steps, and then we can save the model locally and actually utilize the saved model. So you can use the model and then test it. So here I was testing with a prompt where I asked, what are the potential side effects of chemotherapy? And we can see that the model isn't perfect. This could be fine-tuned with more data and it could be improved. So this is just a very rough attempt at fine-tuning with the PubMed QA database. But you're welcome to train for more epochs on your own or utilize this as a starter for your own projects. But in general, I would just note that fine-tuning typically will give results which are not as good as utilizing a RAG-based implementation. So there's a difference between fine-tuning where you're updating the model weights and a RAG-based solution where you're utilizing a vector DB. So now that I've gone through fine-tuning, let me actually jump to RAG and I'll explain how RAG can be utilized. Just to kind of like highlight some of the challenges and considerations of utilizing fine-tuning. So you typically need a pretty powerful GPU to train models like this. You get a trade-off when you quantize these models. So the accuracy may not be as good as utilizing a full precision model versus using a 4-bit quantization. You also need to consider the trade-off from implementing different batch sizes and gradient accumulation as a workaround for larger effective batch sizes. And then for small data sets like this, you can have overfit. So this isn't a really super rigorous data set which covers everything. It's 1,000 samples. So I would recommend utilizing more data if possible, or to prevent overfitting, you can utilize early stopping or increased regularization, or you can augment the data, basically take some of the text and change it into different types of QA data sets. So in terms of improving fine-tuning, you should use larger medical data if possible. You can investigate the idea of continual learning approaches where you train with one set of data and then you continuously retrain and augment the model as new data becomes available. And in terms of applications, you could utilize this as a medical question answering system for professionals. You can use this for literature review, or you can use it as a patient educational tool. It's a very powerful potential model for implementation. It should be possible to combine this with electronic health records as well. So there's a lot of potential applications of this, but there are considerations that should be made when training models like this. You want to make sure that you have a diverse training set to make sure that you're capturing or removing bias. You want to implement fact-checking mechanisms for critical information as well. So for example, if you train a model like this, I recommend that you do a benchmark where you have a human expert evaluate the outputs of the model for a number of tasks before you release it to the world. And it's also important to let people know that they're chatting with an AI and not a person. So that's very important. And you should do regular audits for biases and inaccuracies. Basically, commercial systems will capture every response that is returned to users and actually verify that it is good before it's returned to a user. So utilizing techniques like that would be great. So now that we've talked about fine-tuning, let's actually jump into RAG. So what is RAG? So RAG stands for Retrieval-Augmented Generation, which combines information retrieval with language generation. Some of the key components are a retriever, which finds relevant documents from a knowledge base, and a generator, which produces responses based on retrieved information. So some of the benefits of utilizing RAG are you have up-to-date information without full model retraining. So basically, you create a corpus of knowledge which you attach to a model, which can be used to answer queries. So this provides improved accuracy and factual grounding, and there's transparency through source attribution. So my recommendation is always go for RAG over fine tuning because it's going to be easier, more cost effective, and you can attach documents. So in terms of RAG in a medical context, you could utilize something like PubMed abstracts, medical textbooks, clinical guidelines, or EHR data with proper anonymization. And it provides access to the latest medical research up to what you provide it. And it provides the ability to cite specific studies or guidelines when you return an answer. And it yields reduced hallucination on critical medical information. Some of the challenges, though, are ensuring retrieval of high quality, peer-reviewed information. So either you have to aggregate all of this data yourself, or you need to utilize an API where you can pull this data from something like Google Scholar, etc. And so working with this complex medical data can be a little bit difficult for large language models as well if they weren't trained on medically relevant data to start with. And basically, you're attaching expert documents to something which may or may not be able to return good answers. So you typically want a model which was also trained on medically relevant data to provide the best answers. So for the tutorial that I'll be going through, basically, we're going to be looking at implementing RAG with Llama 3.2. So this is actually the latest open source model from Meta. And the process flow that we're going to be utilizing is the same PubMed QA data set. And we're going to retrieve relevant documents from the medical knowledge base and then return an answer which is generated with the fine-tuned Llama 3.2. So we want to balance retrieval speed and accuracy, and we want to handle long context within the model's maximum sequence length. So some considerations to make when evaluating are the accuracy of the medical information, the relevance of the retrieved documents, and the response coherence and fluency. I always recommend that these type of models be evaluated by an expert to verify that they're good to go before being deployed. And you want to make sure that you have high factual accuracy and comprehensive answers which meet the use of the end user. So for example, if you have a doctor, you can return something which is medically rigorous versus if you're returning answers to a patient, maybe you need to simplify those answers. But let's jump to the code for utilizing RAG. We install a bunch of libraries. We're going to be utilizing ChromaDB for our vector database. So to actually utilize this model, in this case, I'm pulling the model from Hugging Face. So in order to fully utilize this code, you'll need to create a Hugging Face API token, which you'll paste in this code block when it asks for it. So that's just one step that you'll need to take previous. And then we're utilizing the Llama 3.2 3 billion parameter model, which we're quantizing into a 4-bit model. So we're loading the model and the tokenizer. We're verifying the model, and we can see here that we've loaded and verified. So once we've loaded the model, we can load the data set. We're utilizing the Chroma vector DB, which is basically a database which stores the embedded representation of the PubMed QA information. And we're initializing the ChromaDB and ingesting data within it. So we're taking all of the data from PubMed QA, we're vectorizing it, and then we're storing it in the ChromaDB. Answer accurately and concisely based on the given context. We're utilizing the model with a particular prompt template, and we're utilizing streaming in this case. So we set up the full pipeline, and then we can create the QA chain, and we can actually utilize it. And it gives a slightly better response than what we were seeing from fine-tuning. And it provides the actual context from where it derived its answers. So I would say that RAG-based solutions are typically the go-to for live commercial applications and are more trustworthy. So I would recommend utilizing RAG over fine-tuning uh, most of the time. So jumping back to the slides, RAG is great in terms of providing more factual information. Future directions with RAG that could be used in different application cases are for personalized medicine. You could incorporate patient-specific data in the retrieval process. On the back end of an application, you could have this running to where you take in all of the patient data and you use that to create the RAG fine-tune model, and then you can do tailored responses based on individual medical histories. Multimodal RAG is another interesting possibility, especially now with Llama 3.2, where you can do vision fine-tuning. So you could incorporate text-based retrieval with visual information. That is a powerful aspect of the models. You can implement continuous learning where you regularly update the knowledge base with new research and new data. And then you could fine-tune the retriever and generator based on user interactions. Again, ethical considerations, make sure that when you're working with medical data, that it's private, that it's anonymized, and it's very important to provide clear citations for retrieval information. It's also good in general just to let people know they're chatting with a chatbot. I wouldn't recommend catfishing users, so just be very clear about AI-generated content. And that's it for my slides. I'm happy to answer any questions from the audience, and these codes will be provided in our GitHub for use by anybody. You can use these as a starter or just experiment with fine-tuning in RAG. Are there any questions from the audience?
What's the address of the GitHub?
Let me share that with everybody here, just so that you can see it immediately. It's github.com/rcifw/applied-hpc-seminar-series. So this is the URL. I'll be uploading the latest slides and the latest codes here shortly after this presentation. But you can find all of the other presentations that I've given along with the codes here as well. So feel free to utilize these as starters. And if you need one-on-one support, I'm happy to provide one-on-one support as well in terms of getting started with these codes, or if you want to run them on our CHPC, you can contact me as well and we can get you set up there. So my email address is dennis@wustl.edu. And we'd love to have anybody who isn't a user of the CHPC here chat with us if they're interested in running codes like this on our system. We do have free resources and we're happy to onboard you. So thank you. Any other questions go ahead.
Thanks.
Any other questions from the audience?
So Dennis, did you actually try to do any fact checking on RAG versus fine tuning, and kind of for like what's your experience? You mentioned that RAG is much more precise in terms of fact checking, but like you didn't mention any experiments. So did you do anything like to check that?
I didn't do thorough experiments to check the accuracy of these models. This was just kind of something which I hacked together quickly for this seminar. I would recommend doing more experiments with this though. So this is just kind of a starter code. I would say qualitatively, just looking at the responses from the fine-tune versus the RAG model, there was an improvement with the RAG model for sure.
And so there are nodes on CHPC that are ready to do this kind of training.
Any of the GPU-A nodes would be very useful for this. They have A100 GPUs, which have sufficient memory for this type of training. And I would note that utilizing 4-bit quantized models makes this training very quick. So I would say that it takes about an hour or less to train a 4-bit quantized model like this.
All right, thank you.
Any other questions from people on Zoom?
Thank you for the presentation. I just had a question about like, would this work with some of the smaller models? Just in case we haven't actually set up our like the paid partition on the CHPC yet for our lab. So I was just wondering if like switching out the model that you're using for one of the smaller ones just to test out the code would work, or if there's any issues that you think would come up with that.
So I think actually utilizing some of the smaller quantized llama models would work fine on any of our nodes. So I've actually trained or fine-tuned these models on a laptop before as well. So these aren't especially compute intensive to implement within the context of RAG or fine-tuning. You can fine-tune these models on like a M1 MacBook Air. So it would be entirely possible to train these models or smaller models on our CHPC. But I would recommend utilizing quantization.
Thank you.
Other questions from Zoom? All right. If not, we have one question from the audience here live.
Yeah, just wondering for the RAG, if the retrieval database is pretty huge, the very also how much time to generate the response. So then if you have a very huge database, then the retrieval maybe costs a lot of time.
So the question was, with large databases, would it be very time intensive to retrieve answers from a RAG-based method? I would say that RAG is very fast typically. It utilizes vector representations, which are checked to provide an answer via cosine similarity. There's a dot product operation, which is very fast, but it's very fast to retrieve from a very large database. I would say that there's some vector DBs which are optimized for this, but ChromaDB, which I used for this tutorial, would work fine. Well, if there's no other questions, I think we'll close this session. Thank you very much for attending, and these codes will be available shortly. Feel free to email me if you have questions about utilizing them, or if you have interest in starting the project with us or onboarding at the CHPC. Thank you very much and have a wonderful day.